Hello, everyone. Do you hear me?
Yes.
Yes. Okay. So thank you very much for giving me a chance to give a talk to people around the world. And I hope that during this hard time, you will be fine. And today I provide the time to talk about a subject with the we work some year in this project to generate the so-called microscopic optical potential based on some nuclear structure approach to describe the nucleon-nucleus electric scattering at low energy. It means that energy is lower than around 50 MeV. I work with my collaborator, Dr. Kazuhito Miyama, and Dr. Huang Tung from Yutong University. Both of university are in the center of Vietnam, and we work with the support from Vietnam National Foundation for Science and Technology Development. Yeah. So how can I? Yes. This is my city where I'm living. I was born here and I work on here. This is the so-called Huế city in the center of Vietnam. This is the old capital of Vietnam. This is in the middle there is a very beautiful river. And on the right hand side there the place where the king of Vietnam was living for more than 500 years. And then on the left is the modern district where many buildings from French people, American people, building a lot of nice building there. And this is the place where the king was living. And on the right hand side is my university, where it established more than around 60 years before. Yes, we have a small group to work on nuclear physics at Huế University. Here, the image there's some bachelor student and master student, and in the center, me and my collaborator, Dr. Kazuhito Miyama. We interested in some aspect in nuclear structure like fission, and for nuclear reaction, we focus on the microscope optical potential and a little bit about the three-body problem based on the Faddeev-AGS equation. And now, as you know very well, that for microscopic optical potential, we have two main approach with the phenomenological and microscopic. And the phenomenological optical potential is a very useful tool and efficiency tool for describe the nuclear reaction. Most of the nuclear reaction code based on such type of optical potential. And yes, the phenomenological potential is very, high precision, and we can say it's global, like the potential Conning de la Roche potential, for example. However, of course, when we go too far from stability, of course, we can say that it is unreliable when using the phenomenological potential. Yes, and another way to generate the optical potential, it comes from the microscopic approach, and I can devise some many ways to do it, like ab initio from nuclear structure approach, nuclear matter approach, and couple cluster method. You can have very nice review from Dr. Bonacoso and Professor Ditthoff. They do very nice review for such kind of optical potential. And in my approach is based on the nuclear structure approach, which is adapted for the region at low energy. Of course, where the energy is lower 50 MeV, where the structure effect have the structure, the nuclear structure have some effect. The nuclear structure approach has some advantage compared with the nuclear matter approach, which is useful for energy is greater than 50 MeV. Yeah. So I will talk about some results based on the paper in 2015 and some new results which I just obtained some in a short time. Yeah. We can say that the nuclear structure approach, the pioneer is Nicole Whitmore from Paris, Swiss, in 1976. At that time, she only calculate the imaginary part of the optical potential based on the reinforcement of formalism. But at the time, she didn't calculate the cross section and analyzing power. Later, Van Zyl and Bernard, they at Paris Suite also, they are the first group who generate the microscopic optical potential from the SCUM RPA and particle variation coupling based on the SCUM interaction. At that time, due to the limit of the computer, they drop many terms, and they can explain around 70% of the cross section, but they are very soon they can have successful to describe the microscopic optical potential. Later, 40 years later, Guillaume Blanchon with Nicole Whitmore, they come back to this subject again with the Godney interaction, and they obtain a very nice result for calcium 40, calcium 48 for neutron elastic scattering. Yeah. And 2-3 years before, Kazuhito Miyama, he used the osmo, the same approach with the Bernard Van Zyl. Of course, there's only a difference. He used the continuum RPA and continuum particle variation coupling. But with the SCUM interaction, he had a very successful to describe the neutron elastic scattering on oxygen system at the lower energy is lower than 30 MeV. Yeah. And with the help of Professor Van Zyl from Paris, I come back to his subject for years before and try to improve his work and to see if we can have some beautiful result or not. And finally, we can publish in PRC in 2015. Yeah. And yes, as you know very well, that's the potential. Composed for nuclear structure approach, we have two terms. First term here is the Hartree-Fock term obtained from SCUM Hartree-Fock calculation, and the second term we call the dynamic term, with the composed by two terms. The first term is the first order, and the second term is the second order. The first term is obtained from the particle variation coupling. The sigma omega here is the energy of the incident particle, and you can see the sigma is described in this formalism, and here alpha is the single particle state, V here the SCUM interaction, NL is the phonon, here phonon, and here we have a particle and vibration coupling. Okay. And sigma epsilon A is the single particle energy, and the second order here is to remove the effect of Pauli principle violated in RPA calculation. And finally, we have at the end we have an optical potential which is microscopic, generated directly from the SCUM interaction, which is non-local. The non-locality comes from the second term with the dynamical term, then delta sigma here. The potential Hartree-Fock here is local. Its locality is come from the delta character of the delta interaction. Yeah, and of course we have the complex potential, and the imaginary part of the optical potential is responsive for the loss of fluid due to the non-elastic channel. And the optical potential is energy dependent and fully self-consistent, generated from SCUM interaction. So to have the microscopic potential, what I did is first I performed the Hartree-Fock QRPA, RPA or RPA calculation. It depends on the target that I want. For example, if I focus on the double closed shell nuclei, I perform only the Hartree-Fock RPA calculation. And then after I got the statistic from RPA calculation, I will perform the so-called particle variation coupling. on the state 0 plus, 1 minus, 2 plus, up to 5 minus. In our approach, I neglect the unnatural parity, and I limit the phonon energy at lower 50 MeV, because we know that it's due to the limit of the SCUM interaction using in the particle vibration. And the next step, I use this the described formalism to calculate the microscopic potential. And for example, you know that, for example, the dispersive optic potential, they fit at positive energy, and to describe the negative energy, they do the extrapolation. But in our approach, because we use a nuclear structure approach, so the positive and in a negative energy is naturally connected and consistently. So when we want to calculate the imaginary part at negative energy, we just change the energy. We don't need to do any extrapolation. And then to test if the microscopic potential is well or not, we calculate the cross section and analyzing power, angular distribution, total cross section using the DWA code obtained from written by Reina, from CA. And at the end, we will reproduce the elastic scattering observable without ad hoc adjusted parameter. So if it's good, it's good, but if it's bad, it's bad. We don't do any fitting thing. So the table below, for example, of course, I believe that if I want to describe the nuclear reaction the nuclear reaction observable, I need to have the good result, the good information of the underlying nuclear structure information. For example, I perform the Hartford calculation, and I check, for example, the first low lying state, for example, 3 minus or 2 plus, and I compare with experiment. You can see that, of course, I cannot have the so nice result, but it's acceptable. For example, the very strong state like first minus of 3 minus, the B is comparable with experimental data. And when I got this idea, thank you very much to Gianluca Colo and Milan Group, who provide me their code, which is called particle vibration coupling code, which is very at that time very performant. And then based on their work, I can develop the microscopic potential. And when I were in Paris, Van Dijk told me that this is their own result. For example, for the year before, you can see that this on the left panel, you can see this is the imaginary part of the optic potential, and you can see there a peak in the surface around 7.2 Fermi. When you increase the incident energy from 5 to 30 MeV, of course the absorption increase, but you can see that inside the nuclei, when the radius is lower than 6 MeV, then no absorption. And but I think that because this is due to, at that time, in the particle vibration coupling strand, for SCUM interaction, they only had the T0 and T3 term. They neglected the T1, T2 term, the spin dependent term, they neglect the spin orbit term, and yes, of course, Coulomb. Yes, and then also at that time we only have the SCUM S3 interaction, which is very strongly density dependent. So the hardcore inside of the target is very hard. So you can see that at the end they have no absorption inside, but of course they have absorptions on the surface. And on the right hand side, based on the optic potential, they obtain the result for the solid line. I remember they yield the S2 interaction. The dash line, they have S3 interaction at 15 MeV for neutron elastic scattering on lead 208. Then you see that at the small angle, they can reproduce the result, but at the middle and large scattering angle, they fail to reproduce it. So my job is to try to improve their work to see if I can have some positive signal or not. And then what I did is simple. I mean, not too much. For example, at the time the US3 interaction, and of course, 40 years later, I have SL5, which is more modern. Then the alpha, which is density division term, is only 1/6, which is much softer than 1. And at the time, they limit to the 0+. They neglect the 1- for isoscalar, and for isobeta, they neglect the 4+, and 5-, and 3-. And as my time, due to the performance of the RPA and the particle information coupling code, I can have on the natural phonon from 0, parity phonon from 0 to 5-. And energy weighted some rule. For example, at that time, Van Zyl and Bergner get only 72% for 3-, but at that time I can get 100% for 3-. Very nice for me. And then due to I have a much stronger computer, of course, 40 years later, then I can have a larger window, like energy window with the little than 50 MeV. And at that Van Zyl you only T0 and T3 term only of the scum interaction. But for SL5 micronucleation, I have all the term T0, T1, T2, T3, alpha, and Coulomb. And of course, when I compare to approach the only improvement, our calculation is fully self-consistent. Fully self-consistent means that we use the SL5, only SL5, to generate the Hartree-Fock calculation. And then after Hartree-Fock calculation, we get the single particle state, and then we calculate the RPA calculation to get the phonon. And we also use the SL5 to make the coupling between the single particle state and phonon. So SL5 interaction is fully self-constant, and I drop no term during my calculation. And finally, the same difficulty for Van Zyl and Bergner 4 years before. At that time, they must find a way to treat the non-locality by their approximation. But here I have a code, a very useful code of Raylan, and I can put the non-locality inside, and I can calculate it. And at that time, they use universe in offset with the size of the building. Now I only use a simple computer, personal computer, to perform on the double Gaussian nuclei. Of course, even at that time, I had much stronger computer, but the calculation time is time consuming. For example, for ladder 208, if I include the spin-off term, this is a nightmare for me, because I lose around 11 days of working. In Vietnam, sometimes they have the corruption of the electricity, and I would buy a battery supplier for my calculation. Yeah. Then, for example, I compare what I obtained, and I compare with the pioneer work of Van Zyl. For example, the imaginary power of the optical potential of Van Zyl is the green line, and my obtained result is on the red line. You can see that I have a much stronger absorption in the surface, and also I have the absorption inside. Yeah, at 15 MeV. So due to the nuclear structure approach, I can know which the contribution of each state to the imaginary part. For example, the ring color here is 0+ and 1-, and I open more channel. Like now I add 2+, and you can see I know in detail which state is important for the imaginary part. You know, for example, in the case we have a very strong collective state of 3-, with the mainly contribution to the imaginary part. And then I try to analyze my result. For example, at 15 MeV, the red dot here is the experimental data, and the red line, for example, I switch up the dynamic term. I only have the static term, Hardy-Fock, which is the Hardy-Fock term. You can see the red color, the red line is very high compared with the data. But now I open step by step. I open 1-, and the lines go down because we start to have the assumption. And then I open the 2+, 3-, 4+, and 5-, and at the end I have a yellow line here, and which is close to the experimental data. Yeah. And based on the result, some year later, when I have a job, then I continue my research, and then I continue my work. Then I perform all the calculation for on the double closed shell nuclei from oxygen-16 and lead-208. Of course, I don't expect that the microscopic optical potential can reproduce the high precision potential, because it's very high, and I can say from my feeling it is also impossible to compare with the phenomenological potential. But of course, based on the result, I can learn some physics underlying because you know the data, the result is calculated from the Skirm interaction. I don't do any fitting, so you can see the for example, you can see that for oxygen-16 at a small scattering angle, the result is very well. For calcium-40, a small scattering angle, excellent result. Calcium-48, small scattering angle is okay, later also. But for all the nuclei, at large scattering angle, I have a problem. Yeah. Then the reason why I think that because our approach had many limitations. For example, in RPA calculation, we have only one particle, one hole. That's one possible one problem, and there are many problems that I don't know. If I know, I can publish more paper. Then for oxygen-16, for lead, 208, the result is better than the oxygen-16. Then I can understand that the nucleus, the mean field approach, is work very well for the heavy nuclei. For oxygen-16 is less. Then I continue with my work to extend it to the proton elastic scattering, and I have a acceptable result. It's not so beautiful like phenomenological potential, but as small scattering angle, it's okay. It's not too bad. See. And then I always have the problem with the large scattering angle. Okay. And then for analyzing power for proton, for oxygen-16 is not good. And then for calcium-40 is better. For 15 is nice, but for 26 is, the analysis power is very hard to reproduce. 48 is not so bad, and for lead is acceptable, but not. For example, 30, 16 MeV. Okay, and then I try to learn some lesson from the result. For example, I try to think about the sensitivity of the neutron elastic scattering observable on the changing of the interaction. So for example, I change the SL5 and SCAM star to see if they are different. And my conclusion is for two interaction, the result is not so different. So I will study more, but you know, all the calculation is very time consuming. Then if I have more interaction, I can get the conclusion. But actually, at this stage, I can say that it does not depend much on the interaction. If the interaction is fully critical or fully used, we don't drop any term in the interaction. And this is my result from very new for me also today. I try to, because as I said at the beginning, the spin-off bit term is very time consuming. For example, for letter, if I calculate take into account the spin-off bit term in the partition coupling strength, then the time for the calculation is a factor of 10 compared without the spin-off bit term. So I asked myself, for example, Kazuhito Miyama, in his calculation using the continuum partition coupling and continuum IPA, he must drop the spin-off bit term even with oxygen system. Only Guillaume Blanchot in CA, he used the Gaussian interaction and fully comparable with my calculation. Then I asked myself if the spin-off bit term is important or not. If I show it's not important, my collaborator Kazuhito will be very happy. Then I study it. Then for example, the green color is the curve where I turn off the spin-off bit in RPA and particle variation coupling at the same time. And the purple color is the curve where I keep the spin-off bit term in RPA but drop the spin-off bit term in particle variation coupling. And the yellow color is the full. I mean, full is mean that the spin-off bit term is used everywhere. And then you can see as small scattering angle is improved. You see, it's very important, the small scattering angle. At 49 MeV, yes, it improved, slightly improved compared with other, okay? And also at 17 MeV. And people say that the spin-off bit term is important to describe the analysis power, and I want to check it. And of course, overall for 3 energy, you can see that both are not good at all. I mean, but let's see if the yellow color is better than other. Not so really. For example, for 14 MeV, not so really. I mean, even I'm trying to understand by myself. Then I continue with calcium 40 at 3 energy, 9, 10 MeV, 14 MeV, and 17 MeV. At 14 MeV, the region of the giant resonance. And then you can see that yes, the yellow color is seen that is slightly better than other. Okay. And then for the analyzing power, is when taking into account the spin-off bit term, the analysis power is not improved much. See, it's a surprise for me. Okay. For calcium 48 and for lead, yes, see this angular distribution with and without the spin-off bit term, E almost the same. It's slightly improved the spin-off bit term. Okay. And for analyzing power, you can see when taking into account spin-off bit term, it doesn't change much. So at this moment, I think that spin-off bit term is not so important in the particle variation calculation to describe the elastic clustering nuclear reaction observable. But I need more time to think about it. But if it's good, then my collaborator will be happy. So he can drop it, and people can save a lot of time if I confirm it, because midterm calculation is a nightmare, really time consuming. And then I can learn another lesson. For example, if I go to the pairing target like tin 160, for example, and then here E delta is the pairing gap, and I test, for example, I put no pairing, and it's corresponding to the green color. And if I increase the pairing gap in the Hartford BCS calculation, and then sorry, not BCS, but in the RPA calculation, the residual interaction in QRPA calculation, delta is around 1 MeV, and then the corresponding result is by green, the blue curve, and I increase to a crazy value of pairing like 2.5 MeV. This is described by the purple curve, and I see that if I have pairing is small, but it's improved the reaction of angular distribution at the small scattering angle, but at larger scattering angle, yeah, I mean, it's not better. Yeah. So I can say that pairing effect is small, but not negligible to describe the elastic scattering data. Here I plot the imaginary part of the optic potential when I take into account the pairing. For example, the red color without pairing. Okay. And then I have pairing at 1 MeV with corresponding to V0 is 725 MeV with the ring curve. And you see that if we increase the pairing, the absorption increase in the surface, but it's decreased on the volume. Actually, I don't understand why. Why is decrease in the volume? I don't know. But it's surface I can understand, but in the volume I don't understand. I'm trying to think about. And finally, as I go to summary, yes, after some time study with the microscope optical potential, from my thinking, I can say that I convince myself that it's too hard to have a high precision optical potential within the microscope optical model. The only advantage of the approach is which is a natural link between the nuclear structure and reaction observable. For example, I don't need to do any extrapolation to describe the negative energy region. And based on this model, for example, I can study the sensitivity of nuclear reactions observable, which directly depend on the SCRM parameter. And I can say which I will find the answer for myself, which term is important for the reaction observable. And then based on the information, then me and our group can think about how to build the so-called new generation of the optic potential. And for the short term, for example, I can implement the microscope optic potential to the DP reaction code like FADEP AGS equation, because at the form of the optic potential is already separable, which is very useful to use in the FADEP AGS equation. And since the optic potential is already the bridge between the nuclear structure and the reaction. So, for example, for finite AGS code, when you calculate the DP reaction, you must use the for negative energy, you must use the fitting process to get the binding energy, for example, for the target, for example. So now here I use only one potential, but both for negative and positive fusion. And I hope that I can extend it to the inelastic scattering on the double closure nuclei first. So I would like to say thank you to Professor Wang Zai and Gianluca Colo and Professor Khoa, who my collaborator, also my professor, and my collaborator from the university. Thank you very much for your attention.